everybody. So let's finish up this chapter with a discussion of some groups that are not abelian, at least most of them aren't abelian, but they're in some sense the closest you can get to an abelian group from some points of view. And those are called the solvable groups. We aren't going to do much with these, but I would like to at least get the definition and a couple of key examples on the record. So what makes a group solvable? A group is called solvable if it has a sequence of subgroups, one nested inside the other, with the property that each subgroup is normal in the preceding one. So H2 and H1 is normal, and H3 and H2 is normal, and so on. And so that the quotients at each stage, H2 mod H1, H3 mod H2, and so forth, are all abelian. And that's what makes a group solvable. The reason the term solvable comes up is because this is closely connected to a very famous problem of classical mathematics, which is, can you generalize the quadratic formula to higher degree polynomials? In other words, can you write a formula for the roots of a cubic or a quartic or a quintic polynomial? And it turns out that you can for the cubic and quartic polynomials, but there isn't a version of the quadratic formula that just allows you to write down the roots of quintic and higher polynomials. And that fact, by a theory known as Galois theory, turns out to be very closely related to the fact that the symmetric group on 5 elements is not solvable. Is not solvable. So that's why this is sort of culturally interesting. But you'd have to continue in your studies of algebra to learn more about why that fact is true. Anyway, what are the examples? Certainly abelian groups are solvable, because if G is abelian, then you can just take the sequence G and 0, and the quotient, G mod the trivial group, is G, and G is abelian. S3 and S4 are solvable. S3 is a dihedral group, so I'll talk about it in a minute. But S4 is an interesting case. S4 has 24 elements, and it has a subgroup A4 of index 2, which is normal, which has 12 elements, and it consists of all the even permutations. So what are the even permutations? Well, A4 consists of the 3 cycles. Any 3 cycle is an even permutation, and it consists of the 3 products of transpositions. And there are actually 8 3 cycles. 3 of these makes 11, plus the identity element. Those are the 12 elements of A4. And if you take inside A4 this subgroup here, so this is a little, plus the identity, this is a little subgroup of with 4 elements, which is isomorphic to Z2 cross Z2. And inside A4, it's a normal subgroup. And why is it normal? Well, it's normal because the cycle decompositions are preserved under conjugation. We know that. So if you conjugate one of these products of transpositions by a 3 cycle, you're going to get back another product of transpositions. And so under conjugation, this collection of things is preserved, and so it's a normal subgroup. And so A4 inside it has this copy of Z2 cross Z2, and the quotient, this has order 12, this has order 4. The quotient is a group of order 3, which has to be the cyclic group of order 3. So A4 is a solvable group, and so is S4. So A4 is in S4, the quotient is of order 2. And then inside that, you have this group that's isomorphic to Z2 cross Z2, which is the products of transpositions. And then you have the trivial group. And the quotient here is cyclic of order 3. So all of the quotients are abelian. And so therefore, even though this group is not abelian, it is solvable. The dihedral groups are solvable because they have, if you take the dihedral group, it has inside it the group of rotations, which is abelian. And the quotient, dn mod the rotations, is the group of order 2, the reflections. So again, you have a group, this is maybe a simple kind of solvable group where you have an abelian subgroup and the quotient is also abelian. And the example of a non-solvable group is this symmetric group on 5 elements. S5 has a normal subgroup, the alternating group on 5 elements. So S5 has 120 elements, A5 has 60 elements. But I mentioned this earlier. I didn't prove it because it's kind of a pain, but A5 has no normal subgroups, non-trivial normal subgroups. It's a simple, it's what's called a simple group. And so you can't find, it's non-abelian, and you can't find a normal subgroup in here so that the quotient is abelian. And so S5 is not solvable. And that's pretty much all we're going to do with solvable groups in these lectures.